Hi, and thanks for joining me on this talk. In this presentation, we use BGP beacons, network tomography, and Bayesian computation to locate route flap damping on the internet. A common goal in internet research is to measure AS properties on the internet efficiently. Such properties might be filtering of IP prefixes, censorship, or specific traffic engineering policies. The most intuitive way is to actively measure a given AS, inject a signal from one side, and measure the resulting output signal from the other side. But deploying a measurement probe in every single network is simply too inefficient and takes too many resources, especially considering the scale of today's internet. But what we can do is inject a signal from one end of the internet and pick it up at some other point of the internet. And based on the output signal, we can then form a conclusion about a path property. With just one path, we cannot simply pinpoint the node which is responsible for the path property. But if we perform multiple path measurements from different points on the internet, we can solve a simple question and pinpoint the responsible node. Now imagine these two paths, where one has property A, colored in green, and the other one doesn't, colored in gray. In this example, the AS colored in green is the responsible node. Any other node would have also affected the black path. But let's switch back to reality, where measurements introduce noise. In this example, we have got two measurements for the same path, but two different results. This is a problem, and therefore our resulting path data may contradict. Nodes can also behave inconsistently. In this example, the first node has a different property based on the ingress point. For example, in the case of BGP, ASs very often deploy different policies based on their neighbor. So the equation we were just able to solve so easily suddenly becomes extremely difficult to solve because the path data we have measured contradicts and ASs are non-atomic entities. In some cases, the path measurements can lead to no result. This is where because comes in. Bayesian Computation for autonomous systems. It is a solution to this problem which takes labeled paths as input and output probabilities of the AS having a specific property with a measure of certainty. We will explain because later in this presentation. In this talk, we show how we use because to measure deployment of BGP route flap damping using special BGP beacons and route collectors. Let's talk about what BGP route flap damping is. In BGP, routers send announcements and withdrawals to inform the neighbors of a new best path or a lack of a best path to a specific address space. With too many updates, routers experience more load, and this can lead to problems. To prevent this, route flap damping was introduced back in the 90s to reduce CPO load such that the neighboring routers would not have to recalculate their paths very often. Route flap damping is one of the two BGP optimizers to dampen heavily flapping routes. Why should we care about BGP route flap damping? First, if you try to measure noisy prefixes or send actively a lot of BGP updates, for example, to measure deployment of RPKI, route flap damping is a speed bump and thus impacts BGP measurements. Also, vendor default parameters can cause harm and affect internet reachability, so it is useful to know who is using them. Third, there have been too many different parameter recommendations in the past. We don't know what's in use or whether anyone followed the recommendation. Until now, there have been no studies measuring the deployment of BGP route flap damping. As route flap damping can be helpful but also affect reachability, we decided to measure route flap damping on the internet. We use because for pinpointing, but the framework requires labeled paths. So how we acquire these paths is what I'm going to explain now. First, we need to understand exactly how the route flap damping mechanism works. It works based on a penalty, which is incremented with every announcement or withdrawal. Each router keeps a penalty for each peer prefix pair. This plot shows how the penalty may behave over time for a prefix. The red dots indicate where updates are received by the router for the respective prefix from one peer. Each BGP update increments the penalty by a constant. Now you can see that in between the updates the penalty drops again. This is because the penalty always decreases based on a configured half-life. If the penalty surpasses a configured threshold, the suppressed threshold, the prefix gets damped, or in other words withdrawn. Note that the router does not discard further updates, but just doesn't use them. At the end of the blue area, this router stops receiving updates, and therefore the penalty can now go much lower. So low so that it can decrease below the so-called reuse threshold, where the route is considered usable again. As a result, an advertisement of the route is sent. We call this announcement re-advertisement. So you see that we have a time where the router receives updates and a time in which it does not receive any updates. If it would receive an update every, let's say, 5 minutes, it will constantly be withdrawing the prefixes because the penalty never decreases below the reuse threshold. And thus, we would never see the damping AS announcing the prefix. And therefore, we are sending from our beacons a burst break pattern. In burst, we send announcements and withdrawals with a specific update interval, and in the break, we do not send any updates. As explained before, this gives the router time to reset their penalty below the reuse threshold for our prefixes and thus re-announce them. In bursts, we change between announcement and withdrawal with very high frequencies. We have used our own testing prefixes so that we do not interfere with anyone else's traffic. We send the signal and hope that someone damps us. To target different route damping configurations, we are using different update intervals, where 1 minute is the fastest and 15 is the slowest. A small update interval may trigger a more sensitive configuration parameter set, while a larger one may trigger very few configurations. In our study, we sent our beacons from 7 different locations in 7 different networks in the world. We also tried to place our beacons more or less equally spread around the world. Route damping causes a very recognizable update pattern based on which we label paths with route damping true and false. Let's see how this pattern looks in the real world. What you see in these plots are the views from a single vantage point of 2 different paths. Each vertical green line is an announcement. So we are the route collector, and the plots show when we receive announcements for a specific path for this specific peer. The blue areas are the bursts, and the white areas are the breaks. The left plot shows received announcements throughout the entire burst. Everything looks normal. This is what we expect when route damping is not deployed on a path. This is basically exactly what the beacon router is sending. In the right plot, you can see that the signal suddenly stops after half of each burst. This means the route got damped. What you can also see is that there's another advertisement in the break, in the white area. We call this re-advertisement, because this is the point where the penalty drops below the reuse threshold and the prefix is re-advertised. So the left plot shows what a path without route damping looks like, and the right plot shows the pattern route damping produces. And based on this pattern, we label paths with route damping true or false. On paths with route damping true, we know that at least one AS does route damping because someone must have caused the pattern. The challenge is that on a route damping path, the damping AS could be anywhere between the route collector and the beacon. There could also be 2 damping ASs on a given route damping path, not only one. The second challenge is that an AS may only dampen a subset of neighbors. For example, an AS may only dampen peers, providers, customers, or 2 groups. And, as explained earlier, measurements can introduce noise. As mentioned earlier, a solution to most of these problems is because, instead of making a binary decision for each AS, we consider a probabilistic setting. Each AS has a probability value of p. RFD nodes have a value of 1 and otherwise 0. The probability of no node implementing route damping is just a product of probabilities that no one is implementing it on the path. Using this, we can explain the data. We could just do a maximum likelihood estimation, but we may run into problems that we have faced earlier. As we are in a probabilistic setting, we have scope to use Bayesian inference to infer the distribution of the probability that each AS is implementing route flat damping. There are many methods we could consider here to sample from the distribution. Most of them have the same premise. We want to take samples which are possible values of the probability of RFD. We evaluate the probability that these values produce the data. To do this effectively, we use the current sample to take the next sample and walk around the space. We use two methods, one called component-wise Metropolis-Hastings and the other one is called Hamilton-Monte Carlo. The main takeaway is that instead of getting a single value for the probability of route flat damping for each node, we get a distribution that can give us an idea and additionally a measure of uncertainty represented by the variance. If an AS deploys route flat damping, then most of the mass in the distribution is at 1, and 0 if it is not deploying route flat damping. In these two examples, the variance is low, which means we are very certain. On the left side, we find that the center of mass is neither at 0 nor at 1, but the variance is also quite low. This is a good example of inconsistent route flat damping deployment. In reality, AS701 only damps a subset of its neighbors. The right side is an example of lacking data. The variance is very high, so our confidence is very low. A reason could be that this AS is always appearing with another AS on AS paths. The scatter plot shows the average probability versus our measure of certainty. Having these results is good, but we want to make hard decisions on route flat damping deployment for each AS. The easiest ASs are the ones where the probability is high and the certainty is also high. These are ASs that deploy route flat damping consistently. For RFD labeled paths, for which we have not yet labeled an AS damping, are a special case. Here we take the node that is most likely causing RFD. This category mostly includes ASs that are inconsistently damping, like AS701 from the earlier example. On the other end of the spectrum, we label ASs as non-damping if their threshold is sufficiently low. These are also divided into two separate categories. The remaining ASs are put into category 3. These are ASs for which we do not have enough data or evidence or route flat damping deployment is not existent. With dense deployment, what can happen is that an AS always appears with another AS on labeled paths. This makes it difficult to tell which one caused the route flat damping pattern. Overall, this is the result. We say all ASs in category 4 and 5 are using route flat damping, which is in the sum about 9%. This bar plot shows the deployment of route flat damping for each of the update intervals we have measured. ASs that dampen all neighbors we have measured are colored in orange, and inconsistent ones are colored in blue. For the fastest update interval, we have found a deployment of 9%. We have validated our results with ground truth, which we have obtained directly from network operators, because it achieves 100% precision and 87% recall. 9% route flat damping deployment is likely an underestimate, as the 87% recall suggests. For example, ASs that have even less aggressive parameters are only dampened customers are invisible to our setup. We see a clear drop from 5 minutes to 10 minutes in this plot. Cisco and Juniper default configurations, which have proven to be harmful in the past, dampen the 5-minute update interval and faster, so 1, 2, 3 and 5. This means the majority of ASs use route flat damping with deprecated default vendor configurations. We have confirmed this observation with ground truth. The generic because framework could also be used in other scenarios. The summarization techniques can be altered to fit other research questions. Using a new likelihood model can enable the application of this method to network tomography problems beyond the binary problem introduced here. To show that because can also work in other scenarios, we have simulated an ROV measurement and then used because to pinpoint ROV deployment. Because achieved 100% precision but lower recall due to very high ROV deployment. In this talk, we tackled the problem of pinpointing autonomous systems that exhibit a specific property, such as route filtering. We have introduced the generic algorithm framework because. Because uses a set of labeled AS paths and identifies the AS that deploys the property under research. We have showcased because to reveal deployment of route flap damping. For this, we introduced new beacon update patterns specifically tailored to create route flap damping signature to label AS paths precisely. Using because and the beacon update pattern, we found that 9% is the lower bound for route flap damping deployment. We also applied because to verify the deployment of RPKI origin validation. Tracking down censorship and other similar topics might be an application scenario for because in the future. All our scripts and our measurement data are publicly available on rfd.rg.net. Thank you for listening.